I knew this was not going to be quick. Why did I start this? I should have just gone to bed. Hello everyone. Today we're going to be finishing up the recurrent neural network library that we've been building from scratch. The last few things we need to add are making the bias optional. We need to also then go ahead and add regularization techniques. So dropout and L2 are pretty much the only two that I've implemented and that I use. Input times WXH, so the weights connecting our inputs to our hidden layer. What we're going to do is we're going to be adding the whatever's in the hidden layer, and we're going to be multiplying that by the weights connecting the hidden layer together. And then what we do is we add bias at the end. Then we pass that through an activation function. So all we're really going to do is we're just going to have, I guess, an if statement that's just saying, if the bias parameter is true, then calculate bias, otherwise don't. That's what we're going to be doing. It really shouldn't be too difficult, but I have a way to make things much more complex and more convoluted than they need to be. Let's see what breaks. So these bias weights are changing, even though I set it to false. What in the world? Am I going crazy? So this is self-bias. Current weights are 0. So what I'm trying to do now is just confirm whether or not the biases are being randomized or if it's just setting them to 0. So it's setting them all to 0s. Actually, you know what? First of all, let me just do vanilla update. Okay, that I think helps me out and explain things a little bit. So what I think is actually going on is I think this is messing things up. Yeah, right here. There we are. Okay, that's what it is. So for Nestrov's momentum update, you kind of build foresight into it, so you're calculating the weight for the next time step. The formula there is just simply just the bias plus our mu hyperparameter times the variable that we use for momentum. That will create bias weights, even if you don't want them there. And then if I do Nestrov momentum update, 25 minutes in, I think we finally fixed this. Oh my god. Nope. Oh, okay. Well, otherwise, we're just going to set them as that, but we're not going to add anything to them. What the hell? Man, this is supposed to be 2 minutes. This was supposed to be literally just adding one if statement somewhere, and everything was supposed to be fixed. I still have so much to do. Yeah, why is backprop touching back? Oh, okay. So, oh my god. Okay. What we've done, or what we do for Nestrovs, is we create a new recurrent neural network object. And so this new recurrent neural network object, we then call backprop on that. But for this new object, we never actually set this bias hyperparameter. This one doesn't know that bias should not be updated. Okay, boom. That's done. Let's move on to the next thing. So what we're going to do is we're going to create a map, and it's going to mimic the current network that we have. And so, let's say our dropout, we set it to 0.5. So this is our probability of turning off a specific node. What we then do is we then just go through all the nodes within our network, and we generate a random number between 0 and 1. If it's above 0.5, then we leave that node alone. If it's below 0.5, then we turn that node off. So again, because I've already implemented this, I'm just going to copy it. There's no point in trying to figure all this stuff out again. And copying it is like the easy part. Now I have to figure out how to actually implement it. Okay, so now let's actually just draw out what our recurrent neural network would look like. I guess what we're going to do is that we're going to have a mask for this guy, and then we're going to have a mask for these guys. What we could also do is we could also just implement dropout just here after you combine the two of them. What I'll actually do is I'll implement it after the current hidden layer and the previous hidden layer are added together. For vanilla neural networks, what you do is you create your dropout mask after the activation function or so. So in this case, after we passed it through our sigmoid activation function, that's when we then apply dropout, and that's when we then randomly turn off nodes. So by that logic, we should only be applying dropout after we apply our hidden activation function. Every time we do a forward pass, I just need to create a new dropout mask. Just calling this will just always randomly create that mask for us, save that mask, and then finally just multiply the mask that we've created with the layer output. So we're just going to set it to 0s for now. Now, what I want to do is I want to, just as we've done here, go ahead and actually create this dropout mask. Let's assume that these are the output. This is our dropout mask. Essentially what we want to do is we just want to multiply them by each other. Because what we've done is we have changed the output a little bit. So we've taken the output and then we've divided it by our dropout, or our probability, or P active, I'm just going to call it from now on. So probability that the node stays active, just to compensate for the weaker output, we then need to account for this in our back prop. All you're just really doing is when you're taking the derivative, you're just multiplying it by the dropout mass. Let's test it out. Let's see how that goes. Now there's another error. Line 573 over here. Why are you having, oh, it should be dropout mass. Looks good to me. It's training. So that happened with a dropout of 0 because I didn't specify dropout. So if I come here and I specify dropout, so there's a 40% chance that you turn off a specific node. Let's try running that. Okay. I mean, it looks like it's still working. We've gone ahead, we've implemented this. It's still working, it's still training. We don't have any errors. That's one regularization thing done. The second one that I want to implement is L2 error. Each one of these lines will have its own weight. At a very high level, the concept behind L2 error, we are adding the weight, we're adding them to our loss function. And so what this incentivizes the network to do is to reduce the weights as much as possible. What happens if we have a really large weight for one node? Well, if you have a really large weight for one node, that's essentially just the network trying to memorize data that's in the training set. So here's our plan of attack. We're going to implement an L2 for loss. And so what that's going to do is we're essentially just going to grab our weight all weights within our network. We're just going to summarize them and we're just going to add that to the loss. That's the first thing we need to do. The second thing we need to do is for each of the individual weights. So in our case, in our recurrent neural network, we have weights connecting our input to the hidden layer. So that's WHX. What we're going to do is we're going to take our delta for WXH and we're going to subtract the sum of all the weight, and then we're just going to multiply that by our lambda, which again, lambda is just a parameter controlling how much to penalize. High lambda, you want to penalize it for large weights. Low lambda, you don't want to penalize it for weight. But I guess what's confusing me is they do the deltas, because remember in the RNN, it's one. We have one hidden layer, but that hidden layer, we pass values through it 4 times for each of the time steps. So it gets used 4 times. I knew this was not going to be quick. Why did I start this? I should have just gone to bed. What am I talking about? It doesn't matter. What we're doing is we're only adding or subtracting it from the weight, from the deltas, right? Except for the bias. So it's only the weights that we do L2 for. We don't do L2 for the biases. Oh, pretty interesting. Okay, let's go to the neural network that I've already created before. In the vanilla neural network, it makes sense that you add it because you have essentially just like one output, right? And so with that one output, then you can go ahead and you can add L2 to it. But for a recurrent neural network, you have multiple outputs over time. For each input that you add to the network, you have the one output associated with it. And so you can then go ahead and you can then add L2 to the error and blah, 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 blah. But for the recurrent neural network, all these are essentially, yeah, sure, they're different inputs that you put in, but they're all pretty much just the same thing. You're essentially just putting in letters to say the word hello to the network. And what it's spitting out is different outputs over time. Does that really matter? Or am I just tired? If you try to relate this to our recurrent neural network, let's say that these are all different outputs, different points in time. And so what we do is let's calculate the L2, or let's add L2 to the loss or to the error for every point in time. What we're going to have to do is we're just going to have to manually calculate the L2 error for each of our specific weights. So all we're doing is we're just looping through the weights that connect the input to the hidden layer. We're looping through each and every single one of them, and from there we're then calculating our L2, and then we're dividing it by lambda. So we've implemented this part. This part is all good. Now what we need to do is we need to go ahead and we need to implement the deltas down here. So in the recurrent neural network, what happens with the deltas is you have a delta for each time step, and then what you do is you add all the deltas together. So that will give you the final set of gradients that you have. And then you just add those to your weights, and that's how you update your weights. For standard neural network, yeah, you're not adding gradients together, and so you just have the one delta that you calculate, and then you go ahead and then you add the L2 portion. So I guess the question I have now is, do we add our L2 for each time step, or do we add our L2 at the very end? Because remember, L2 is essentially just the weights that we're adding to it, right? So if you add the weights too many times, then the gradients are going to get fairly large. But I do think that we should do it for every time step, because when we're calculating the loss, we calculate the loss for every time step. So we only need 3 because remember, once again, we don't calculate L2 for the biases. Let's test it out. Oh, I didn't get any errors, but it didn't train. I'm very, very suspicious that there were no errors. Okay, let me stop dropout. Okay, there we go. Essentially, we've implemented L2. It's not broken. It's still training. Still learns how to say hello at the very end. Oh man, this series is going to become a lot longer than I thought it was going to be. Hello everyone. Today we're going to be finishing up the recurrent neural network that we built. I'm really worried because I'm going to look at this library in, let's say, 6 months time, and I'm going to have absolutely no clue what I've done. Everything that I've learned to build this and make sure it works, I'm going to come back 6 months later and be like, what is all this gibberish? So oh, the spider's still there. What the hell did it do? Did it jump? Oh, sorry, I'm getting distracted by a spider. What was I doing? I'll just pretend I didn't see that and just move on. It's too late for that. Oh, okay. Are we done? I think we're done. Can we please be done?